In this lecture, we're going to develop the finite element method to allow us to solve for two-dimensional stress-strain problems using triangular elements. But before we do that, I think it'll be useful to review our derivation of one-dimensional bar elements using the principle of minimum potential energy. You'll recall we're trying to solve for a bar with a node at one end we'll call node 1 and a node at the other end we'll call node 2, and we're trying to find the displacements at node 1 and node 2. What we're really trying to find is an approximation for a function ux, which is the displacement anywhere along the length of my bar. We assumed, because we don't know what this function is, we're going to assume the simplest thing we can assume. We're going to assume that it's a linear function. So we assumed that u, a function of x, the displacement anywhere along the length of the bar, is equal to some constant a1 plus some other constant a2 times x. We found, using something called Lagrange polynomials, that we could write this expression, having solved for a1 and a2, by using a linear combination of linear functions. We could write this expression in this way as two vectors multiplied by each other. Remember how we solve for a1 and a2. We're saying, for the moment, let's pretend we know the value u1 and u2 at x equals 0 and x equals L. We plug that information in. Now I can find a1 and a2 as functions of u1 and u2. Regardless of how we find these shape functions, we can write them in this form. And I can write these as two different shape functions inside a shape vector. So I have n1 and n2, which are my shape functions. I call n my shape vector. Once I have this approximation for u as a function of x, my displacements along the length of the beam, I can start going ahead and trying to find relationships or ways to express stress and strain using this approximation. To find strain, remember our strain in the x direction is defined as du dx. Since written in this way, u, a function of x, all my x dependence is within n, all my information about my nodal displacements is in this vector u. When I'm trying to solve du dx, that just becomes the derivative of n, my shape vector with respect to x, and we called that derivative my b vector. So I can say my strain in the x direction is simply the derivative of my n vector, my b vector, times my displacement vector. Once I have strain, I can find a relationship for stress, because stress is defined by Hooke's law simply as Young's modulus times the strain. So my expression for stress is just E times the expression I already found for strain. Okay, now that I have stress and strain, I'm ready to start developing an equation for the total potential energy stored in my system, in this case, my system being just an individual bar with some forces applied to it. My total potential energy consists of the strain energy inside my bar, and I'm going to subtract off all of the lost energy due to external forces that are acting on my body, but those forces are being used to create the strain energy. So here's my expression, which we derived for the total strain energy stored inside the system. Notice it has stress in it and it has strain in it, and I just found formulas that I can plug into this for stress and strain. We also had these two terms for the external energy, potential energy due to the external forces. This integral expressed the energy due to any type of distributed load or traction load along the length of the body, and these two terms represent any forces being applied at the nodes. Taking these two terms for my total potential energy, and now I can substitute in the expressions I derived earlier for stress and strain, I get this form. Notice this expression has a vector u here, and this expression has a vector u here. This expression has a u and a second u, and therefore this expression turns out to be a quadratic in terms of u. Our next step, now that we found an expression for the total potential energy, is to take the derivative of the total potential energy with respect to my displacements. And we spent an awful lot of time on in-class assignments proving that you can do this as a series of the partial derivative with respect to u1 and the partial derivative with respect to u2, or you can look at these as vectors and simply take the partial derivative of potential energy with respect to the u vector. It ends up being the same. Here I have a quadratic form. This is like u squared, so when I take the derivative, it simply becomes 2u. I have a 1/2 here. That cancels out. These two terms just have a single individual u and an individual u. When I take the derivative, it's just whatever the constant is in front, and the u goes away. So after I take the partial derivative with respect to u, and I set my partial derivative to 0, I get this form, which is the form that I need to solve for my unknown displacements given knowledge of the external forces. This is what I referred to as the finite element, finite element form using the principle of minimum potential energy. We've gone through this quite a few times. Why am I doing it now? The reason I'm doing this now is we're about to embark on the same process for two-dimensional elements or two-dimensional triangular elements. I want you to see that what we're about to embark on is essentially the same as what we've already done. Now we're just doing it in 2 dimensions. In the following videos, we'll start going through this derivation. I will leave up on the screen our one-dimensional variation, or the part of the one-dimensional variation that corresponds to what we're doing in the two-dimensional derivation, so you can see and compare the differences. And we'll start doing that in the following videos.